What if the next big leap in AI reasoning, that kind of tackles really complex problems, didn't actually need a massive supercomputer or a huge budget?
Right, what if you could achieve it with, well, pretty modest hardware and on a real shoestring?
Sounds a bit counterintuitive, maybe, but that's exactly what we're diving into today on the deep dive. We're looking at some fascinating research that suggests a much leaner path for AI.
Exactly. We're unpacking the paper TINA, Tiny Reasoning Models via LoRA, and it really does present this remarkably cost-effective way to significantly boost how well language models can reason.
Okay, so why should you, our listener, care about this? Well, this research gives us a glimpse into a future where really powerful AI isn't just locked away in giant data centers.
Yeah, it suggests advanced reasoning could become much more accessible. That could spark innovation in all sorts of, unexpected areas.
We're definitely talking about some potential aha moments here, especially when you see the kind of power they unlocked with such efficiency.
So our goal today is to really dig into the core innovations and the key findings from this TINA research. We want to understand precisely how they managed to get strong reasoning performance using what they call minimal resources.
Okay, let's set the stage. What was the fundamental challenge these TINA researchers were trying to solve?
Well, the central problem is making it economical to give language models robust, multi-step reasoning abilities. Historically, this has been pretty expensive.
Right.
You either have supervised fine-tuning, which needs tons of expert data and might just teach mimicry, or reinforcement learning, which is powerful but usually very computationally intensive.
So big data sets or big compute power, where does TINA fit in? How do they approach it differently?
Tina took this really elegant minimalist approach. Two key things. First, a tiny base model, just 1.5 billion parameters. It's the DeepSeek R1 Distill Quen 1.5B model.
1.5 billion? That really is small compared to the giants we usually hear about.
Tiny. And second, they use parameter-efficient post-training, specifically LoRA-based reinforcement learning.
Okay, a small model trained efficiently for complex reasoning seems almost paradoxical. Why that specific base model? Was there a strategic reason?
Oh, absolutely deliberate. The hypothesis was that this particular model, because of its DeepSeek and Q roots and being a distilled version, likely had a stronger starting point for reasoning.
Ah, so starting with something potentially already a bit smarter in that area.
Exactly. It lets them better isolate the effect of their RL technique. Plus, using a small model dramatically lowers the costs and computational needs, makes it much easier for others to experiment too.
Right, lowers the barrier to entry. Okay, small, clever base model. How did LoRa-based RL boost its reasoning without needing, like, a warehouse full of GPUs?
This is really the core innovation. They used low-rank adaptation LoRA. Basically, LoRA freezes the original model weights,
Okay.
and then it adds these small trainable matrices, think of them like adjustment layers on top. These low-rank matrices, A and B, allow you to change the model's behavior quite significantly, but you're only training a tiny fraction of the total parameters.
So instead of tweaking billions of knobs, you're just fine-tuning these small add-ons. That sounds incredibly efficient.
It is, and the paper really hits this point hard. They say, notably, LoRa enables the modification of a model's behavior by training only an exceptionally small number of new parameters.
Which fits perfectly with their goal.
Exactly. They continue. This dovetails with our central motivation, achieving reasoning capabilities through the most economical means possible. And they contrast it with other methods, saying, while most existing open models that enable reasoning rely on the more expensive full parameter training, we investigate the use of LoRa.
Highlighting the novelty. Okay, LoRa brings the efficiency. Why use reinforcement learning specifically for reasoning tasks?
Well, reasoning tasks often have a clear right or wrong outcome. Think about a math problem or a logic puzzle.
Yeah, the answer is either correct or it isn't.
Precisely. That correctness provides a really clean, verifiable reward signal for RL. The model gets feedback positive reward for right answers, negative for wrong, and learns the strategies that lead to success. The paper notes this too. Reasoning tasks are well suited to RL paradigms, as the correctness or quality of the final output often provides verifiable reward signals.
Makes sense. The final answer is the judge. Did they use a particular RL algorithm?
They did, yeah, a GRPO-style algorithm. GRPO stands for Group Relative Policy Optimization. It's a variation of PPO, but what's neat for efficiency is that it removes the need for a separate value network.
Ah, streamlining it further.
Exactly. Less computation, less complexity, which again fits that whole minimal resources theme. It's quite an elegant setup.
So, small base model, efficient LoRa training, streamlined RL algorithm. Did this minimalist combo actually work? How was the reasoning performance?
The results were frankly quite compelling. The Tina model scored between 48.16% and 50.60% on average across some really tough benchmarks.
Which ones?
Things like AIM, AMC, MAT 500, GPQA, Minerva, these are respected datasets for testing advanced AI reasoning.
Wow. Okay. Nearly 50% average on those benchmarks with such a small setup. That's genuinely impressive.
It really is. The paper states the results compellingly demonstrate the efficacy of our economical LoRA-based RL strategy. They achieved, quote, substantial reasoning aptitude.
And crucially, how did they compare to the base model before this RL training?
That's another key point. They explicitly say significantly nearly all TINA models notably outperform their corresponding baseline average scores. So the parameter efficient RL definitely added significant reasoning capability.
And the cost. I remember seeing the numbers in the paper, doing a double take.
Oh, it's remarkable, truly. They estimate the cost to reproduce their best TINA checkpoint was just $9 USD.
$9.
$9. And to reproduce all their experiments, everything in the paper from scratch, around $526?
That is astonishingly cheap in the world of AI model training.
Absolutely. And they did this on just two NVIDIA L40S GPUs, even co-locating training and inference on the same hardware to be extra efficient.
Okay, incredible results for minimal cost, but why did it work so well? The paper has this really interesting hypothesis about rapid format adaptation.
Yes, this is a central, very innovative idea in their work, the rapid format adaptation hypothesis. The core thinking is that LoRA is especially good in this context at quickly teaching the model the output format needed for reasoning.
Like how to structure the answer, step-by-step thinking, that kind of thing.
Exactly. Many reasoning tasks benefit from that chain of thought or step-by-step structure. LoRA, they argue, learns these structural patterns very efficiently with minimal parameter changes, crucially, while preserving the base model's underlying knowledge.
So it's learning the style or the structure of reasoning output without having to relearn all the facts and concepts.
Precisely. They contrast it with full fine-tuning, where updating everything might be less efficient and could even risk messing with the stored knowledge. LoRa's targeted updates seem ideal for just adapting the output format.
The paper puts it quite clearly, right?
Yes, they say we posit that LoRa excels in this scenario because RL for reasoning heavily rewards the model's ability to generate outputs in a specific, verifiable format or structure. LoRa appears to be highly adept at learning these structural and stylistic patterns with minimal parameter changes, thus requiring very few FLOPs. It's a key insight into why it's so efficient.
That's a really cool hypothesis. Did they find any evidence for this during the actual training process?
They did. They looked closely at the training logs and saw this distinct phase transition. Metrics related to the output format, like the reward for getting the format right or the length of the output, showed a relatively sharp change or turning point during training.
Okay, so the model sort of clicks and figures out how to structure its answers.
Kind of, yeah. But interestingly, this format-related transition didn't usually line up perfectly with a sharp change in the accuracy reward. Accuracy tended to improve more gradually or fluctuate.
So learning the right format happened relatively quickly and distinctly.
It seems so, and here's the really insightful part. The checkpoints with the best reasoning accuracy also occurred just before or right around this format transition point.
Just before or around it, what does that imply?
It suggests that while learning the correct output format is crucial and LoRa does it efficiently, just optimizing purely for format beyond that point doesn't necessarily lead to better reasoning. It might even hurt performance slightly.
So there's a sweet spot. Get the structure right, but don't over-optimize the format to the detriment of the actual logical steps.
Exactly that. It's a nuanced balance. The paper notes this. We consistently observe a training phase transition or turning point evident in the format-related metrics.
Right.
And then the key implication, the fact that peak reasoning accuracy is achieved just before this format-driven transition implies that while learning the correct output format is essential, pushing further on format-centric optimization alone does not necessarily yield better reasoning and may even be detrimental. It's valuable guidance.
Fascinating. Okay, beyond that core hypothesis, they also ran ablation studies, right, to kind of dissect the different components. What innovative things came out of those?
Yeah, ablation studies are always crucial. They found several interesting things. One big one was about data. Smaller, higher quality data sets could actually outperform larger ones.
Really? Like how much smaller?
Well, they had one model, Tina OpenRS, trained on just 7,000 curated examples. It actually beat Tina OpenR1, which was trained on over 93,000 examples.
Wow. So quality over quantity, especially for reasoning, it seems.
It really underscores that, yeah. It's not always just about throwing more data at the problem.
What else did the ablations reveal?
They looked at learning rates for the LoRA training, found that while it matters, they got good results without massive tuning, suggesting some robustness. A rate of 1e6 worked well in one setup.
Okay.
They also tested the LoRA rank, basically, the size of those little trainable matrices. They found that low ranks, like 16 or even 32, were very effective. Rank 16 actually hit the peak performance in one comparison.
So even the small adjustment matrices were powerful enough. Reinforces the efficiency point.
Definitely. And finally, they compared their RL algorithms, GRPO and Dr. GRPO. Both reached similar peak performance, but Dr. GRPO seemed to get there a bit faster, suggesting potentially better sample efficiency.
So across the board, the minimalist choices seemed justified and effective. And the researchers really wanted to make this accessible, right? The open source aspect.
Absolutely, that's a major emphasis. They see the TINA project as democratizing this kind of research. By making it reproducible and super cost effective, they're lowering the barrier for others.
That's great for the community.
Totally, and they backed it up by open sourcing everything. The code, the detailed training logs, even the final model weights and checkpoints, they explicitly state it's in service of accessibility and open research. A big contribution in itself.
Fantastic. Now, no research is perfect. What limitations did they acknowledge? Where could things go next?
They were upfront about a few things. First, the 1.5B parameter model, while efficient, probably has a limit on the absolute complexity of reasoning it can handle compared to, say, a 100B parameter model.
Sure, there's likely a ceiling.
Right. Second, their evaluation focused mainly on math and logic problems. How well Tina's skills transfer to other areas, like creative reasoning or common sense problems, needs more study.
Domain specificity. Makes sense.
And finally, they mentioned doing minimal hyperparameter tuning deliberately to show the core method's effectiveness and low cost. So there's likely room for improvement with more fine-grained optimization.
Standard limitations, but good to acknowledge. Okay, let's try and wrap up the key takeaways, the core innovations here.
Sure. So fundamentally, Tina shows you can get surprisingly strong reasoning in small language models very, very cheaply. Using LoRa-based RL is innovative in its sheer efficiency.
Right, performance competitive with potentially much larger, more expensively trained models.
Exactly. And the rapid format adaptation hypothesis is a really novel explanation for why it's so efficient. LoRa learns the output structure quickly without disrupting existing knowledge.
And that training phase transition provides neat observational evidence for it.
Uh-huh. Plus, the findings from the ablation studies, like data quality over quantity and the effectiveness of low LoRa ranks, add valuable academic insights. And finally, the commitment to open science is huge.
This has been genuinely illuminating. It really pushes back against the idea that cutting-edge reasoning needs behemoth models and budgets. So here's something for you to chew on. Given Tina's success, how might this ultra-cost-effective approach change AI research?
Could it really democratize access, letting smaller labs or even individuals make significant contributions to AI reasoning?
And could that core principle, efficiently learning structure while preserving knowledge, be a key to unlocking efficiency in other AI domains too, beyond just reasoning?
Lots to think about there. Definitely some fascinating possibilities opened up by this work.
Absolutely. And as always, we strongly encourage you to check out the original research if this piqued your interest. We'll have links to their Notion blog, the code, the logs, the models, everything in our show notes. Thanks for joining us for this deep dive into Tina.